Imagine a simulated city environment, monitored continuously from above. Traditional security camera grids share a critical limitation. They are passive. They record video, but they rely entirely on human attention to identify when something goes wrong. An operator watching multiple screens will eventually miss key details. Human fatigue leads to oversight, and even when an incident is spotted, the time it takes to dispatch physical security can be the difference between a resolution and a failure. To a standard camera, a person waiting for a train looks identical to someone loitering with intent. These systems lack the built-in intelligence to distinguish normal behavior from a suspicious act. Improving urban security requires moving past passive recording toward an active, AI-driven pipeline, one that can identify anomalies in real time and autonomously dispatch a mobile robot to investigate. Before a single piece of hardware is deployed, this entire autonomous system is built and tested inside a virtual environment. In a software-in-the-loop architecture, the exact same software branches into two testing environments: digital simulation and physical hardware. The simulation uses a custom gazebo world modeling an indoor facility with boundary walls, moving actors, a surveillance camera, and a mobile robot. Deploying a virtual Turtlebot 3 inside this space allows engineers to observe how the robot navigates and reacts to events, ensuring strict behavioral fidelity without risking damage to physical components. This environment allows for the validation of production code under controlled, repeatable conditions, isolating software bugs long before the robot ever navigates a real hallway. The base of this software stack is the hardware itself, running on Ubuntu 22.04 Linux. Sitting directly above the operating system is ROS2 Humble. Rather than a traditional operating system, ROS2 is a communication middleware, the pipes that allow different software programs to talk to each other. It uses DDS, a decentralized protocol where components connect directly over the network. The smallest unit is a node, an independently running process handling one specific responsibility. Nodes communicate by sending messages directly to each other through a named data channel called a topic. This operates on an asynchronous publisher-subscriber model. A node broadcasts data to a topic without needing to know which other nodes are listening or if any are listening at all. By separating the communication layer from the specific hardware, this decentralized middleware allows developers to build modular robotic behaviors. The active surveillance workflow begins at the fixed overhead camera. This camera captures video at 30 frames per second, publishing the raw image data to a dedicated ROS2 topic. Our custom perception node subscribes to this video feed and processes each frame through a YOLO V8 deep learning model, snapping bounding boxes around every detected person. To understand intent, the node uses pixel velocity thresholding. It calculates how fast a subject's bounding box moves across the camera frame over a set period. Based on this speed calculation, the node categorizes every person into 3 distinct states: walking, running, or staying. The perception layer distills high-bandwidth, unstructured video pixels into low-bandwidth, structured behavioral data. A rule-based decision engine then subscribes to that behavioral data stream. The logic is temporal. If a subject's status remains staying for 5 consecutive seconds, it is flagged as suspicious. There is a gap between what the camera sees and what the robot knows. The sensor identifies a person using 2D image pixels, but the navigation stack requires 2D physical map coordinates to investigate. Rather than relying on hard-coded positions, the system solves this dynamically using a homography transformation. A 3x3 projection matrix takes the pixel coordinates at the person's feet and mathematically maps them onto a uniform, real-world grid. The engine formats these precise physical coordinates as a standard ROS2 pose-stamped message, publishing it to the navigation goal topic. This geometric translation eliminates the need for preset waypoints, allowing the robot to dynamically target any anomalous location. Once the goal coordinates are broadcast, a custom 3-stage navigation pipeline takes over, replacing the standard Nav2 planners. First, an IA star planner computes a raw, collision-through route from the robot's current location to the target, navigating around any static obstacles. That raw path is a series of jagged waypoints, which are immediately passed to a dedicated path smoother node. This smoother applies a cubic spline algorithm, refining those sharp angles into a continuous 200-point curve to prevent robotic jerking. Finally, the Smart Path Controller takes this newly generated smooth curve and translates it into physical wheel velocity commands to drive the robot. This controller uses a hybrid approach, automatically selecting model predictive control for high speeds on straight lines and switching to pure pursuit logic for sharp turns. Throughout the journey, an AMCL localization feedback loop continuously checks the robot's laser scanner against the map, updating its precise position in real time. Separating the planning, smoothing, and controlling functions into individual nodes creates a curvature-aware navigation stack that is efficient and responsive. We can trace a single suspicious event from its initial optical detection through the temporal logic check, down to the final velocity commands driving the robot's physical arrival. This architecture powers the sequence, routing data from YOLO to the controller. Components interact exclusively via standardized topics like goalposts. Because of this decoupling, swapping the camera for a thermal sensor requires zero altered code in the navigation stock. This strictly decoupled, software-in-the-loop approach reveals the core utility of ROS2. It allows us to build complex, resilient systems in simulation, ensuring they are fully validated before they are deployed in the real world.